Right, here we go. Sensors. I'll have a little look at sensors in this session. Types of digital sensor, types of positional sensor, and talk a little bit about selection, some pros and cons of some of them. Obviously, I ain't got time to go through all types of sensor, so this is a little bit like the stuff about stepper movers, where I'm showing you about something, giving you an idea about the level we should be looking into it to, and then you can apply that to whatever sensors you choose to look at for your assignment. Okay. So, sensor technology, sensors, transducers. Transducers are a word often used when you're transducing from one kind of physical quantity to another. So you're more likely to call it a sensor when it's transmitting from or translating from a pressure to a voltage or a current, or from a flow rate, where you've got a change of physical medium. But they're sort of interchangeable. But depending on the quantity we want to measure, so we can measure things like light level, temperature, force, pressure, position, speed and sound. And in each of those there's quite often a wide range of sensors available to be able to measure. For instance, temperature, we've got thermocouples, we've got thermistors, thermostats and resistor temperature detectors, to name but a few. Position, which is something we're looking at with regard to the assignment, and that's an angular position of the rotating turntable and the linear position of the situation as well. We've got potentiometers, we can use encoders, reflective slotted opto switches and LVDTs. I'm going to have a little look this afternoon at encoders and LVDTs in particular, and also a brief look at where we're using sensors that measure an analog quantity, one that's infinitely variable between two limits, then just discussing the basics of the need for analog to digital conversion so that we can process it. The purpose of any sensor is to provide some kind of output, usually electrical output in terms of mechatronics, that's dependent upon a physical change that's happening in the world. The temperature's changing, the pressure's changing, the flow rate's changing, the weight's changing, and so on. For example, we might want a digital sensor on a door alarm, be on or off depending on whether the door is open or closed. So that's a simple digital sensor, only on or off. Pressure sensor may provide a varying voltage signal dependent upon the pressure in a tank or in a pipe or at a valve. Sensors are available in a wide range of types to suit a wide range of applications. They've all got their advantages and disadvantages, but the main aim of sensing any quantity is so we can use it to control a system, usually these days via a microprocessor or some kind of computer or PLC. Digital sensors provide an on, off or on output dependent on a single physical condition. It shouldn't be confused with a sensor that provides a digitized output of an analog signal. Sometimes with a larger sensing device, there'll be some analog to digital conversion built within it. Okay? Some typical digital on-off sensors are things like limit switches or micro switches, proximity switches, both capacitive and inductive and magnetic, and then photoelectric type switches, where we sense something moving past a beam of light or such like. Okay. If we look at limit switch and micro switches, there's a really wide range of styles and types available depending on what you want to do with them. The main advantage is that they're simple, they're robust, and as a unit there's a positive physical contact, so you can see whether whether a piece of equipment's making contact with and pushing the wheel down, and they don't require any power supply to operate. They are a clean set of contacts. The main disadvantages with them is because they're mechanically operated, they have a finite mechanical life. The contacts have a finite life as well, and you can get dirt and moisture in them under certain conditions. They can be broken by physical contact due to poor alignment. So if you don't line the switches up right and you've got a piece of heavy moving machinery, you can quite easily damage the mechanism, and it can be difficult to make them accurately adjustable. So you ain't going to be like stopping a hydraulically moved system accurately by setting a limit switch very easily, because there's a tolerance in the switching. Inductive proximity switches. They're used for non-contact detection of metal objects. So the operating principle is that there's a coil and an oscillator create a magnetic field around the sensor head. The presence of a metallic object within the sensing area dampens or changes the field, and then there's an electronic circuit inside there that's monitoring the field, and it detects this change, and when it detects enough change, it will switch over an electronic or transistorized output to turn it on or off accordingly. The advantages of this is that they are non-contact, so they will not disturb the product or the system on the system that they're being used. So if you think about your water bottle passing, if that's a metal object passing, the fact that it's not going to touch it means it ain't going to slow it down or displace it on the conveyor, where a limit switch would. Some types have adjustable sensing distance, and they can discriminate between metallic and non-metallic objects. And you've experienced that discrimination when you've done the PLCs, because you had the inductive sensor to sense only metal objects. We used that as a metal detector, didn't we, to chuck out or stop the conveyor if you got a metal product go through. Whereas the other sensors will only sense that they won't sense plastic, but other sensors will sense metal and plastic. So the disadvantages are that the sensing distance is relatively small, have to be quite close. From my experience, within 10 to 15 mil of the sensing head, the metallic object, and some types require a separate power supply so that they can operate the electronics inside them. So in that sense, there are some types of these sensors, that's the sensor, that require 3 wires. They got a plus and minus to give it a power supply, and they got an output. There are other types, generally running on systems where you just put the limit switch in, and then you can run a relay directly off that. There's no separate power supply. It takes its power supply from the system you're using it on. So that's the sensor. That's a control relay, but that could just as easily be a PLC input. So there's 2 types. There's 3 wire. Sometimes go on to 4 wire because you'll have a normally open or normally a closed style operation you can set it for as well. Okay, so you'll have 2 outputs. But there's a wide range of types that you can get, and a wide range of typical usage of such things. Capacitive proximity switches. These are used for non-contact detection of metallic and non-metallic objects. The principle here is there's a variation in capacitance between the sensor and object being sensed. Because when an object enters a preset distance from the sensor, an electronic circuit begins to oscillate. When the oscillation reaches a certain level, it switches over. So here we're not looking at a magnetic field, we're looking at a disturbance of the capacitance. Non-contact, okay, again, so don't disturb the product on the system. Some types have adjustable sensor distance, can be used in conjunction with inductive types to discriminate between metal and non-metallic objects. Again, the sensor distance is relatively small, and they, like the other type, the inductive type, can require a separate power supply. Magnetic proximity switches. Similar principle, operated by the presence of a permanent magnet close to the switch. These aren't electronic. They've got a reed switch in them. This pull that are got thin reed-like plates. They're sealed in a glass bowl with an inert gas, so they don't corrode really. There's no physical contact with these. Sealed contacts have a higher life expectancy. They've got a small size, are sealed against ingress of dust and moisture. They do still have a finite electrical life, the contacts, and they require a switch and magnet mounting. Typical things will be like guard switches, where you've got these magnets that go into proximity into the switch and actually switch it, the reed switch over. Photoelectric. 4 types, and we'll look at that on the next slide. They all operate by using the light sensitive elements and are made up of some kind of emitter or source of light and a detector or receiver. An object between the light source and its receiver causes electronic circuit to switch an output on or off. Main advantages is there's a very wide range of types, sensing over a long distance in some cases. They're non-contact. Main disadvantages is, and this is from my own experience really, such a wide range of types available that it's difficult to choose the right one. They can be tricky to align and adjust, and from my experience of working in a food factory where there's a lot of water about, they can be affected by moisture and indeed dust as well. So trying to set them up when there's a lot of moisture about in a food factory where people have been cleaning, and you get there's quite a nightmare. I mean, there's lots of other types now that will sense different colours and all sorts of different configurations that you can get. These are then classed in 4 different, 3 or 4 main types. Direct reflective. The emitter and receiver in one housing. So within this housing, there's an emitter and a receiver. The emitter sends out a beam, okay, and if there's an object in front of it, the beam is reflected back into the receiver, and therefore it turns the output on or off, as the case may be, because most of these you can change them round so that if there's an object it turns it on, or you can have it if there's an object that turns it off. Then you can have reflection with a reflector called retroreflective types. Again, emitter receivers in one housing. Requires a reflector. The object interrupts the beam, so the beam is normally going out to the reflector and coming back, and the object intervenes between the reflector and the sensor and trips the output. Again, it's an on or off situation. Polarized reflection with a reflector is similar to the above, but the polarized reflector offers an advantage that allows more reliable sensing of shiny objects, and they're less likely to be upset by random reflections from other places. So it's just one that's designed to use in more tricky situations where you could get some interference with that sensor. And then the last type is where the through beam, where the emitter and the receiver are in separate housings, for instance either side of a conveyor, and again there's a beam constantly going between the two, and you're looking for the beam to be broken to trip the switch mechanism. All of these are electronic, no moving parts and non-contact, so they have those advantages as well. What we move on to now is positional sensors, which is more down to the nitty-gritty of what we're looking for in the assignment. Measuring position, measuring rotation. Potentiometers can be used for this. Linear variable differential transformers. Encoders. These all provide an analog output, variable between limits. I'd argue a little bit about that with encoders. That's a little bit of a mistake for me to put that on there. But certainly the LVDT and potentiometer would be given output between limits. For example, 0 to 10 volts. This would be in proportion to a variation in some kind of physical quantity between limits, i.e. you'd get a 0 to 10 volts output for a pressure varying between 0 to 10 bar. Okay, so there's a little bit of throwback there from a previous year about measuring a position of a hydraulic cylinder over a linear range. Okay, but you could use a potentiometer to do the rotation of a turntable. You wouldn't use an LVDT for that, but you'd use that on a cylinder movement for sure. So, potentiometer. What a potentiometer consists of is some kind of conductive or resistive track. This is the circuit symbol for it, and you have a voltage plus and 0 volts either end of the resistive track, and then a wiper moves along that track, and therefore you can vary the resistance between there and get a variable output voltage between the 0 volt terminal there's a voltmeter in there and there. So as this moves up and down, if this is max 10 volts, as that moves up and down there, we would get a varying voltage here between 0 and 10 volts. Yeah. So the output voltage comes off the wiper. You can get there's rotary types of potentiometer. What you're usually going to be looking for in the type of applications we're talking about is something that varies linearly as it goes round the track. So for every 10 degrees you want the output to change by the same amount. You want a linear output, not some kind of curve. Okay? Lads, I'm recording, so can you keep noise down, please? But as well as rotary types, you can also get a straight type. So it looks almost like a linear pneumatic cylinder. but inside there's a pair of tracks so that you can connect it to a hydraulic cylinder, and the potentiometer moves linearly. So what you've got there is a track like this, and then you've got a rod, so you've got a connector to that, connected to some kind of rod that's fixed to something that's moving. This is moving backwards and forwards, and you've got your 10 volts this end and your 0 volts that end, and that's created an output by moving up and down the track. Something like that takes up more room though than a rotary potentiometer. Also with rotary, you can get types that are multi-turn. So therefore you could put it on something that's going to go round more than once, and you can actually get a much longer. But then you're looking requiring a mechanical gearing mechanism to operate those. Yeah. Potentiometers, main advantages: low cost. Certainly the rotary ones are low cost, low tech, easy use. Disadvantages are that they got moving parts, so they wear mechanically. The accuracy is quite low. The repeatability of a particular reading at a particular distance is not that good. The sensing range is limited by size unless multi-turn with gearing is used, and cheap carbon track types are subject to electrical noise. So, you know, you've got to keep these. We used to have the linear ones, and they almost. Have you got one of the side lockdown? Yeah. Sorry. We have the linear ones, and that's like a hydraulic cylinder. That's almost lifting a stainless flap up on the top of it, and you would get grease and oil ingress into that, and that would cause loads of issues as well. But you know, it just depends on the application which type you pick. But they're okay as long as you don't want them. As long as repeatability, absolute repeatability and accuracy is not an issue. Linear variable differential transformer. What these consist of is 3 coils, and then inside the 3 coils you've got a ferrous or a magnetic material, nickel iron according to this diagram. So we got some kind of linear motion of that iron core. Now, the way this works is you've got a primary winding which you excite with AC voltage at a particular frequency. I believe they're normally between about 1 and 10 kilohertz is the frequency used for these. Okay. When the thing is in the middle, the 2 secondary coils are wound what's called anti-phase. What that means is they're wound so that the magnetic fields are equal and opposite to each other when the core is in the middle. So when the core is in the middle, you get an induced voltage in each of the 2 secondaries, but these voltages 180 degrees out of phase with each other, and I'm going to show you a little animation in a minute that shows how that works. So when it's completely in the middle, and you've got the same amount of core in both of the secondaries, the outputs from both secondary coils are equal in magnitude, but 180 degrees out of phase with each other. So effectively, they cancel each other out, because the overall output, if we draw a graph of these 2 outputs, if this is the left-hand coil, when that's in the middle, that's the left-hand coil. This is the right-hand coil. and at any point, if you add those two voltages together, you get nothing. So the actual output of the system, when that's in the middle, is a flat line along there, no output at all. And then as it moves either side, you get an output. And they work it so the actual output is a sine wave, but you get a linear portion either side, or a close to linear portion either side, that they use for the effective output of this system. The output is an AC waveform, an AC sine wave, that they then rectify into a plus or minus DC signal. Okay, so these are quite good sensors in terms of showing what's going, being able to detect position. So there's another slide that sort of repeats what I just said, really, but in the middle, these two are anti-phase from each other, so the output is nothing. We move to the left, and we get an output like so, which is in line with that one. And then if we go the other way, we get an output that's shifted back the other way. So we've got the voltmeter in the middle, to the left and to the right. And if we just take a quick look at this little link here, as that core moves, you can see that the output, the pink one at the bottom, is going up and down. These are the two. This is the primary excitation on this coil here. So as it moves, if I grab this, if we move towards that as the middle, if we move towards the blue one, you can see the blue output becoming bigger, the green one becoming smaller. Yeah. And therefore the output is close to the blue one. And you go the other way, the output is doing it perfect there. Closer to the you get the idea that as that position moves, you get a phase change as well as an amplitude change, and that use that to detect position. So if you rectify this output with some diodes, you've got a DC that's going either side of a zero. Yeah? And then you can use that to measure position. So, LVDTs, pros, frictionless measurement. That because that core is made to go as an air gap between the ferrous core and the coils, that's completely frictionless in operation. The resolution, there's no steps in it that can infinitely measure the position. So it's not a stepped measurement. It's got an infinite mechanical life because there is no friction. There isn't any mechanical hysteresis involved that you would get with a switch. So it will measure the same if it's travelling from either direction, really, is what that means, Danny. You've got no float in it. So if you come from the left or you come from the right to a position, you'll get the same reading. Very repeatable. It's environmentally robust. These things can be immersed in liquid. You have to buy the right version, but they're capable of being immersed in liquid and still operating. And they're insensitive to radial movements of the shaft. Doesn't really matter if that core turns or if the thing moves radially. They are sensitive to temperature, They're not really feasible for right long measurements greater than 500 mil. I've certainly not seen one that big. I mean, where I've seen them used is on the plastics machines I used to work on. They'd sometimes have a variable head where the thickness of the plastic could be made thicker and thinner as you try, because what you do is you extrude a long tube of plastic to make a bottle, and that comes through a die as a pin inside a die, so you've got a small gap, and they'd move either the pin or the head up and down to open and close that gap, and they use one of these LVDTs to control the opening and closing of that, because you're only moving it, you probably ain't moving it no more than about 2 mil maximum travel, but these will do that. You can get quite a big variance in output if you want to for quite a small movement in distance. They aren't, although they got this linearized portion, they aren't that linear in operation, not perfectly linear in operation, but then nor are many things. So they're pretty good sensors for linear movement, sensing linear movement. Right, rotary encoders. They are sort of resemble potentiometers, but they're non-contact optical devices. Can be used for converting the angular position of a rotating shaft into an analog or digital data code. They work on a similar principle. The light from an LED or infrared light source was passed through a rotating high-resolution encoded disc that contains the required code patterns, either binary, grace code or BCD. Photodetectors scan the disc as it rotates, and an electronic circuit processes the data and gives you an output, okay, which can be a stream of binary output pulses fed to counters or controllers which determine the position of the shaft. Two distinct types, incremental and absolute. So the incremental type are the less sophisticated type, and that can be a round disc, but this diagram helps to show exactly what's going on a little bit better. Imagine being laid flat, really. There's two, if you have two sensors creating two square wave pulses, because as this chart here moves in front of those sensors, it's going to sense the holes in the disc. Yeah. If you have two sensors creating these pulses 90 degrees out of phase with each other, it can then sense which direction it's going in. Because if output A is coming on first, and then B is moving in one direction, if B is coming on first, and then A is moving in the other direction. And you can count these speed pulses, to detect how far something's moved. You can also sense the frequency of the pulses to determine what its velocity is, so you can detect its speed. Okay? Any questions, Danny?
No.
Yeah? So, these two outputs are often called quadrature outputs because they're 90 degrees out of phase for each other. Okay. Now, the other thing about these is the number of segments or slots determines the resolution of the device. So, when you're thinking about your turntable in your assignment, what is depending on the minimum angle you want to be able to detect, will determine how many holes you need in your disc, really, so that you can to determine how many different positions you can sense. So unlike the LVDT here, you have got a minimum step that you can detect with this type of device. Okay. If you you major disadvantage of incremental encoders is if you're using them for position, they're good for measuring speed. But if you're moving them from position, you're going to be using some kind of external counter from an initial starting position to determine where it is. If it doesn't know where it was when it started, then that doesn't know where it is precisely. Do you understand what I mean by that? So, the trouble is, if it's moving and the power goes off, it's lost. It doesn't immediately know where it is. It would have to go back to a home position first, and then move again to where it wants to go.
It's got to reset itself.
Yeah, because it's measuring incrementally from an initial known position. If it loses where it is because it loses power, that would then have to reset itself back to a home position. So if you're thinking about a machine, that would have to move to its base position, confirm that was there, so that then knew where it was again. Yeah? One way to overcome that situation of it not knowing where it is to use absolute position encoders. What these do is they provide a multi-bit code that is unique for each position that you want to detect. So the more bits you have, the more positions. So in any position on that scale, this is creating a unique code in that what you saw the other week. 4 zeros, 3 zeros and a 1, 3 zeros and 2 zeros, a 1 and another 0, and that can be in binary code or grayscale. Yeah, but the thing about it is, if that thing stops, it loses power. As soon as that's turned back on, because that's a unique code, it knows exactly where it is. Doesn't need to return to home position. Okay. So you only get the same code once in each revolution of the disk. And that's an example of one. Most are single turn, so they got one set of codes for it to turn around once, but there is possible to get versions that have got multiple disks and therefore can detect more than one rotation of a shaft. Now, just to distinguish, Danny, between binary code and grayscale code. If we look at the top one, you'd get a binary code that would give you a direct binary code for quick conversion to decimal as we go round there. If we look at this one, here we got 4 ones. If we say the weight is 1, 4 ones, this would be 4 zeros. We got 1, 0, 0. As we go round there, we got a binary code. 4 zeros, 3 zeros and a 1. That don't look like it to me. You got 2 things changing at once on here, I thought. It looked like a grayscale to me. Yeah. Here's where we can see there could be. What the issue is as this disk is returned, from that point, from that code there, 0100 to 0011, more than one thing is changing at a time. More than one of the bits is changing at a time. So, if that bit switching doesn't happen absolutely simultaneously, you're going to get errors. Yeah? Whereas, if you go for the grayscale, if you look at this, there's only one bit changing there. There's only one bit changing there. There's only one bit changing there. Only one bit changing there.
This one is grayscale.
Yeah, that's grayscale. Yeah. So what that means is you're avoiding the bit switching error because only one bit changes at a time. The issue there is that would then require, because what we really want is for it to go through a binary code like this, starting at 4 zeros, and so on. Yeah. What a grayscale does is it doesn't go through that. It goes, for instance, to and so on. Yeah. So it's not a binary. It's not what would normally be accepted as a binary number in a computer. So that needs some extra logic to convert from this grayscale, this one, to that. So it requires some extra software, programming, or logic circuits to do that conversion. Right? So, moving on then from that, we've talked about one or two sensor systems that's going to give us an analog output. That's going to be measuring an analog variable thing like pressure between 0 and 10 bar, or temperature between 0 and 100 degrees C. So there's a number of types. There's your LVDT or your potentiometer that gives you an infinitely variable signal. For instance, 0 to 10 volts or 420 milliamps. For these signals to be used by computerized systems, they invariably need to be digitized. Note that the digitization of analog signals also reduces the effect of external noise on that signal. So, if you've got an analog signal and you send it long distance as an analog signal, it can really easily be interfered with from other signals. If you digitize it into a series of ones and noughts, effectively, that is far less susceptible to being interfered with. The process of converting analog signals to digital is called analog to digital conversion, or ADC. There is also, whilst not the subject of today's session, there's the opposite of that. So if you've got a PLC, you want to control something that needs a variable voltage, you'll have digital to analog conversion as well, which is going the other way. Right. So, A to D conversion, two-step process. The first step is quantizing, breaking down the analog value into a set of finite states. Then we encode it, so we assign a digital word or a number to each state and matching it to the input signal. So we take discrete steps for the original signal and we assign a binary code to them effectively. So, first step of quantizing. If you have a 0 to 10 volt signal, separate them into a set of discrete states with 1.2 volt increments. how do we get one to 0.25 volts? Well, that's on the next slide. So we got if we've got 8 output states, any voltage between 0 and 1.25 volts will be state 1, and then 1.25 to 2.5 state 2, and so on. Yep. Where that 1.25 volts comes from is here. The number of possible states that the convert output can have is n is equal to 2 to the n. So where n is the number of bits in the A to D converter. For example, if you've got a 3-bit A to D converter, n is 2 to the 3, and you've got 8 discrete steps. So we have to divide our voltage range, 10 minus 0 volts, so we've got a 10 volt range, divide that by 8, that's where our 1.25 volt steps come from. So from that, we also, this is the encoding, we assign a digital value or a binary number to each state. So 0 is your 3 noughts, 1 is 1, 2 is 010, and so on. So we got this binary output that we talked about. So not the grayscale, we apply a binary number to it. So that we can then say as no volts, 1 volt, 2 volt, 3 volt, and so on, or whatever we want it to be. Accuracy of A to D conversion. There are 2 ways to best improve accuracy of A to D conversion. One is increasing the resolution, which improves the accuracy in measuring the amplitude of the analog signal, and the other is to increase the sampling rate at which we measure the voltage. So I got one missing, have I? Or have I just do the step one?
You go step 1. No?
No, I haven't.
Okay.
So the resolution bit can be increased by the resolution is the number of discrete steps. So we always said that the quantization size is the voltage range of a 2 to the n, where n is the number of bits in your converter. So in a previous example, Q is 1.25. If a lower resolution would be if we used a 2-bit converter, we'd then be 10, so that would be 10 over 2 to the power 2, we'd get 2.5 volt steps. So we'd have less accuracy or less resolution. If we increase the number of bits to 4, then we're dividing 10 by 16, and each voltage step is 0.625 of a volt. So you can see quite quickly, if you add bits to your ADC, you're quite quickly going to reduce the step size that you're representing your voltage with. But however many bits we'll have, we'd always have some amount of quantization, what's called quantization error. The left-hand image is 3-bit with 8 steps, and we were representing a 0 to 10 volts. The straight line going up the middle is what the actual voltage is we're trying to represent, and you can see that there's an error plus or minus half of what the step size is. So if our step size was a volt, here, if these steps are 1 volt each, then at any point we've got an error that could be plus or minus half a volt away from what it is. The only time that's as exact is when it's halfway up the step. So by increasing the number of bits, and that particular diagram I picked out was a 5-bit, which gives us 32 steps, you can see that the quantization errors are that much smaller because of the extra number of steps that you got to represent the voltage. Sampling rate. Okay. If you sample, the idea is that if this is the AC analog signal we're trying to represent, if we sample it not often enough, we don't get a very accurate representation of what the original one is. Yeah. If we sample it a lot, we get a better representation. Of what the real one is. Yeah. So you can get an error if you frequency at which the ADC evaluates the analog signal, as we see in the second picture, evaluating the signal more often, more accurately depicts the signal being put into the ADC. So again, if we sample at much higher frequency, take more readings of what the actual analog signal level is, the more likely we are to be able to reflect that signal accurately. So if we sample far too slowly, what we get is where the input signal is changing much faster than the sampling rate, we get what's called aliasing, where the signal you're getting, or as your output from the analog to digital converter, as an alias of what the actual signal is, as in that bottom diagram there. Whereas if you adequately sample, you get a good sample signal. And there's a rule called the Nyquist rule, where you should try and have a sampling frequency that's at least twice as high as the maximum frequency in the signal you're trying to mimic or trying to digitize. So if you're expecting frequencies up to 2 kilohertz, you really need to sample them at 4 kilohertz to get a reliable representation of that signal. Yep. Overall, if we do both, you get overall better accuracy. So increasing both the sampling rate and the resolution by having more bits in your ADC, you're always going to make it that much closer to what it is. So effectively what you're doing there is you're making the steps on the y-axis smaller by having more bits, and you're making steps across the time frame smaller because you're sampling it at a faster rate. Overall, you're going to double the effect of improving the representation of that signal. So it's a double gain there if you increase the sampling rate and increase the number of bits. I have a feeling that the Mitsubishi PLC number of bits on the analog to digital converters is 12, I think. So 2 to the 12. $4,096 steps. I don't know what the sampling rate is. I'd have to check that out. But 4,096. If they are 12-bit, and I think they're 12-bit, 4,096 steps. So you divide a 10-volt signal up between that. Your steps are about 2.5 millivolts. And that's my presentation on sensors, or on some of the sensors that are out there anyway. Right? Any questions?
No, it seems helps give a push in the right direction as well. For the
Yeah.
time.
Yeah.